So welcome back. Hope everybody had a good weekend and is doing well today. And any questions up front? Questions on PA1, questions on Git, so on and so forth. Because we're going to start some new stuff today. Well, let's clear up any issues so far. So I've had a few people asking about Git, having trouble with repositories and pushing things over and so on. So let me just mention this again. Few things to keep in mind. Number one, ideally, every time you start a new project, a new assignment, a new whatever, start in a clean directory on your Linux system, okay, and start a fresh repository on GitLab. Okay, don't just have one directory called 223 that you do all your work in, because every time you push something over, it's going to push over everything that's in there, and it's going to make things complicated, and you're going to have to keep renaming your repository and so on. So when you start PA2, make a PA2 directory, make a repo CSE223 PA2, hook those together with the git remote add origin, and then just just work in there for PA2. If you want to write some test code, make a new directory for test code, make a new repo if you want to push it over to Git, and so on. Don't be afraid to use the resources. Alright, GitLab has tons of space available. It's free to use, 10 gigabyte limit per repository, so take advantage of that. And Linux, partition things up in a way that makes sense, but make sure you partition them. Because that'll usually work well. The other thing I want to say is just, whenever you start a new project, day one, first thing you should do is, make the clean directory, do a git init, make a readme or something, git init, git add, git remote add origin, git push origin master, go over to GitLab, set me up as a reporter. Do that like in the first 5 minutes of a new project, and you don't have to worry about it again, okay? Just make your edits, work on your files. Every time you want to push it over, git add, git commit, git push origin master. Okay. PA2 and forward, I'm going to release this restriction about only having your main class file in the repository. So if you want to have practice files and sample files and things like that, you can just push them all over, and that'll be fine. So I'll make that clear on PA2. Alright, so hopefully Git is working for people. And we'll find out tomorrow morning at 8, but make sure you get everything submitted and pushed over and get me added as a reporter by 8 a.m. tomorrow morning. Okay, that's when I'm going to do my big download. So let's move on to new stuff. The goal this week is to start talking about and thinking about the idea of objects as actually being objects, okay, as being more than just data. So when we have a linked list in 222, we think of it as a sentinel node and a bunch of pieces of data hooked together with pointers and stuff. In an object-oriented mindset, we want to think of that linked list as more than just the data. We also want to think of it as the code, the methods that we will use to manipulate that data. Okay, we want to view those as being part of a bundled whole, which we call an object. And Java makes this really easy to do because everything is basically an object. And so PA2, the challenge there is going to be thinking in this mindset of objects are collections of data bundled with code. Okay, so we're going to play around with some built-in objects today. Some classes. So I want to start with a class called LinkedList. Okay, and LinkedList is, it comes in your Java install, and it's actually java.utility.linkedList. So we're going to have to import that. Okay, and a linked list is, it's a linked list like what we did in 222. So we can construct a linked list, and then we can start doing the following. We can say add. That's a method that adds an element to the end of the linked list. Okay. We can also add to the beginning with this add first method, which adds an element to the beginning of the list. We can zero out the list by saying clear. That removes everything from the list. We can also add and particular location. If we wanted to add something to the third element of a linked list, we can say add parentheses 3 comma element. And a couple of things here. One, this is the same name of the method that we use for just adding to the end of the list, but remember, methods are different if they have different arguments. So this is a fundamentally different function, but it does the same thing as an add, except we get to specify a location. The next thing to note is that this is a little better than your average run-of-the-mill linked list, because linked lists, normally you can put in the beginning pretty easily. You could traverse to a location and insert there, but if you wanted to insert after the third element, you'd have to write a little loop, which says 3 times go ahead and follow from the sentinel to the first node to the second, and then insert after the second. Well, we have a method built in to do that. Add, you could just say 3 comma element, and it would put it into the third position, indexed from 0. We can retrieve the first element, the last index, or the element at a particular location. So get index, get first, get last, right? So we can kind of use our linked list like an array. We can put in an index and actually pull an element off of that, but we can also get to the last element, which is presumably efficient because it's probably implemented as a circular array, so we don't have to traverse the entire list to get to the end of it. We can also search for elements. We can specify an object and say, tell me where that is located, and it'll give us the index or location where that element first appears, or -1 if it's not in the list. And so this is a linked list like what we wrote in 222, but it has a whole lot more features. For example, it's got a pop and a push. If you wanted to use your list as a stack, we can use these two methods. We can remove the head or first element of the list. We can use this thing as a queue. And we saw that, stacks and queues can be implemented with lists. Well, we can use this linked list and treat it as a stack or as a queue. We can replace an element. We can say set the element of this index to be this new object. We can find out how many things are in the list, and we can turn our list into a plain old array. So a couple of things to think about at this point. One, there's a whole lot of functionality here, right? A whole lot of ways we can interact with the list that have been provided for us by whoever wrote this. Number 2, we're on the other side of the firewall now. In winter, we were writing the linked list class, right? And I was asking you to present to the user, which was your main program, an interface, a very specific collection of functions that would be called to interact with your list. And we had this idea of an abstract data type, which said to somebody using your data structure called a linked list, they just see initialize and insert and search and traverse and so on and so forth. And we didn't want the main program looking at the implementation details. Well, now we're on the other side of the window, right? We are the main program. We are the user of this data structure, and we have no access to the underlying details. Maybe there's a sentinel node, maybe there isn't. We have no way to access that if there is. Maybe it's a circular list, maybe it's a doubly linked list. We have no way to know that. Maybe it's not a list at all. Maybe it's an array. And when you insert something in the middle, it just moves everything down the way that we described when we started 222. We don't know that, right? All we know is that if we want to insert something at a particular position, we can use these methods. We can say add an element at index 3, right? Or we can say add an element to the end of the list. And we know what these will do because the documentation tells us appends a specified element to the end of the list. But we don't know how it does this. And that's important, right? We're not required to know, and the details of how it does this should not affect the code we write that uses these methods. Okay, this is part of information hiding, one of the key ideas of object-oriented design. So somebody hands you a class and says, here's a linked list class, right? All you have to know is, how do I interact with it? You don't have to know how it's actually implemented. You don't have to know what's going on under the hood. All right, so we want to move into this mindset of thinking about working with classes in terms of this unified interface. And we already do this, right? I mean, this is kind of what happens when, you know, when we work with a string, for example. We want to know the length of a string. We say string.length. And we don't know what it's doing. We don't know if that length is stored somewhere or if it's, you know, counting until it finds a null terminator. In fact, we don't even know how strings are stored. Are they stored with a null terminator? Are they stored as a collection of characters with a variable that says how many characters are in the string? Are they stored in a linked list, right? We don't know. We don't care. It doesn't affect us. All right, so keeping that in the back of our minds, let's play around with the linked list class. And let's start to get an idea what kinds of things we can do and how this idea of a list being an object is going to be useful. And this is going to be what PA2 is about, okay, sort of working with this mindset. So I'm giving you examples here, but they're examples that are going to come back in useful ways. So we need to introduce one concept here, which is new, which is the idea of a generic. So normally, you know, we talk about integers and doubles and strings and rectangles. And when we make a linked list, we could have a linked list of integers or doubles or strings or even rectangles, right? But if you think about the linked list code that we wrote last quarter, we usually wrote linked lists for integers, but if we wanted to write a linked list that stored strings, not that much has to change in our code. Right? Now in our node we have to say, you know, string data instead of integer data, or double data, or float data, right? But the actual manipulation of the list really doesn't depend on what kind of object we have. When you want to insert in the beginning, you say, you know, make a new node, set the data equal to your data value, set the next equal to sentinel next, set sentinel next equal to our new node, right? And nowhere in there does the fact that our data is a string versus a float versus an integer come into play. So the linked list class can handle different kinds of data. And we use the same linked list class whether we're making a linked list of integers or strings or doubles or any other kind of object. And so this is something called a generic. And when you look at the documentation, what you'll see is my presentation. There we go. When you look at the linked list class, what you'll see is class linked list, this angle bracket E sitting off here. Okay, that E tells you that this is a generic class. Okay, it takes a generic data type. And what we do is if we want to make a linked list of integers, we're going to say linked list angle bracket integer. If we want a linked list of strings, we're going to say linked list angle bracket string. All right, so let's play with this. So let's make a linked list main.java. The first thing we have to do is we have to do an import java.utility.linkedList. Okay, that's like our include that tells it where we can find this linked list class definition. So this is class LL_main, and I'll say public even though it's automatically public. And we'll make a main program, public static void main string args. Well, let's make a linked list. So linked list is the type of variable, and I don't know, I'll just call this list equals new linked list. All right, so this is how we normally declare an object. Type of object, variable name equals new, and then type of object, right, the class name. The only thing is we have to specify what type of linked list we want. Linked list of ints, linked list of strings, and so on. The constructor, we don't have to specify any arguments. Okay, if we just want an empty list, we can just use paren. But we have to specify this type. So the way this looks is as follows: linked list angle bracket integer equals new linked list angle bracket integer. And that's all we got to do. Okay, so the only time we have to do this is when we declare an object and when we construct it. So it's just this one line if we do them both at the same time. And from there on forth, we just have our object called list, which is a linked list. Okay, so list is now a linked list of integers. So let's add some stuff to the list. My typing is really not on point. So list.add, I don't know, let's add a 7. List add 17. List add 23, so we're just doing some prime numbers. And list add 101. Alright, so I'm just using this add method to say add an element to the end of the list. Okay, so now our list should contain 4 pieces of data. Let's check the size. So I'm going to call the size method of list. I'm just going to print out list has length, and I'll show what the size is. And we'll call it good right there for now. So let's compile that. Let's run it, and it tells me list has length 4. And if I had done this before I added anything, right, then that first time would have said length has list 0. So not too startling there. So let's look at some elements of the list. So let's get the first element of the list. Well, if we look at get, there's a get first and there's a get last. So let's get first. And this should give us a 7. All right, so that's the first element of the list. And if we get the last element of the list, that's our 101. So this variable list we can think of as, you know, this thing that has functions associated with it, right? It's a linked list, but mostly it's a set of functions for interacting with a linked list, right? So normally we think of variables as data, but we can actually think of it as a way to get to all of the functions that we want to use to interact with that data. So to add something to get the first or last element and so on. So we can also do something like iterate over the elements. So we can loop over from 0 to less than or equal to the size of the list. And there's a get method, which we can just pass an integer and it'll give us the element at that index. So now we can loop over each element and print it out 1 per line. And so elements 0, 1, 2, and 3 are as shown. All right, so we added stuff to our list. There's also an add last if we want to add something to the end of the list. So let's do that. So now, oh, we're normally adding to the last, so let's add to the beginning of the list instead, because normally adds to the end. So if we insert in the beginning, we're basically making like a queue or a stack. We're getting things in reverse order. So the first thing that we added was the 7. Well, that got pushed all the way to the end because the last thing we added, 101, got added to the first entry, element 0. So this is doing, the stuff we talked about when we're trying to insert into the middle of an array, except, it's presumably a linked list internally, and so it's not actually moving things around in memory. But if we just thought of this as an array, right, we can put things in between other things, and stuff gets moved around to make space, which is pretty powerful, right? Pretty useful. So even if we didn't know what a linked list was, we could store data and retrieve data efficiently using these methods. Okay, and in the morning section, I made versions of all of this code that you're seeing, different specifics, but same idea. And I put each one in a separate file and pushed it up to the upload area. So today this afternoon, I'm just going to keep changing this one file. But the different versions of it are available in the upload area from Canvas. So we could make a linked list of strings just by saying linked list string. And so we have to make some strings. So there's 4 strings we're adding to our list, and we're adding them in the beginning each time, so this will come out in reverse order again. But compile it, run it, there's our linked list of strings. And the only thing we had to change was this and this. That's it. Okay, plus, we had to add strings instead of integers, but, to create this list, just specify a different type in the declaration and the constructor, and then all of this stuff still works verbatim. And in the documentation, you'll see add first takes an element E of type big E, right? That's the type parameter that you specified up here when you constructed your linked list. So if you say linked list string, you can read this as saying add last expects a string called E, right? And appends a specified element to the end of the list. And add last, it says, is equivalent to E, which we noticed. All right. And speak up if anything along the way seems weird or strange, or any questions or anything like that. Otherwise, we're just going to keep going with this, okay? So we've got linked lists of integers and linked lists of strings. Well, we made a Java class called Rectangle last week. And it was just called RECT. You can construct with 2 doubles. You can construct with no arguments, which makes a 1x1 rectangle. Or you can construct with a single argument, which makes a square whose sides are that length. And it's got an area method and a perimeter method. It's got accessors and setters. And it's got a toString method, which prints out, height by width. Let me simplify this a little. Let's just have the toString method return the height, a times, and a width. Okay. And let me compile that so I don't forget about it. All right. So what if we wanted a linked list of rectangles? Right, that's all you got to do. Just change these to say this is a linked list of rectangles. So I can construct a new rectangle, which is 5 by 7, and I can use that as an argument to add first. Let me just do add. And now I can add a bunch of rectangles. I can add a 7 by 7, I can add a 1 by 1, and I can add a 4 by 6. And we're going to have a linked list with 4 rectangles in it. So 5, 7, 7, nothing, and 4, 6. And this one I'm going to put somewhere special. Or not. Okay. So let's go ahead and run this. And, you know, first element was 5 by 7, last element was 4 by 6, and there's the ordered list of elements: 5 by 7, 7 by 7, 1 by 1, 4 by 6. So even though rectangle is a class that we created ourselves, right, we can push it into this other object, object of type linked list, and it will take those things in and do the right things. If we say add a rectangle, it adds those. If we say get element 2, it gets element 2, and that's a rectangle, and it prints that out using the toString method of the rectangle. And the thing I want you to remember in all of this is that if this is a linked list of rectangles, then this is a rectangle. This is a rectangle. That is a rectangle. Right? It says list.getLast. It's running a method, but what it returns is a rectangle. So we can do something like this. Right? We can say, let's take list.getI. That's a rectangle. Rectangles have an area method. How do we run it? We say name of the rectangle dot area. So this whole thing will tell me the area of rectangle I in our list. Right? So element 3. Did I not compile? I did not compile. There we go. So element I is something by something whose area is, and there's the area of each rectangle. Okay? Hopefully you're thinking of this as something pretty powerful, right? It can be a little mysterious that this actually works, but that's a good thing. I mean, this is what we want. This is the idea of objects. It's encapsulating the data and the methods into a single thing, right? In this case, you know, a rectangle. All right, let me make a different version of this. Let me go back to integers. So back to like our earlier version. Right, so this was just our original version where we put some elements in and we could look at them. Let me show you something else that you can do. Let's just do this. Suppose we just say print out list equals and we append list to that string. Now we started talking about toString last week, and the idea was if you take any kind of object and you append it to a string, it calls that object's toString method. And it should turn it into some kind of useful representation. Sometimes, you know, it just shows you the name of the class, an @ sign, and then some hex numbers. But if we have a linked list and we append that to a string, what does it look like? It looks like a linked list, right? It says list equals, and that string that's returned by toString is a pair of angle brackets with a comma and space separated list of the elements of our linked list with no comma after the last one. So this was our traverse function, right, that we used for looking at the elements of a list. Well, in Java linked list, if you try to append it to a string, it calls the toString method, and what the toString method returns is something that looks like this, which is a very nice, you know, easy to read representation of your linked list. So that's kind of cool, but that's not the coolest thing. Let me show you the coolest thing. If we go into LL main and we were making rectangles, let's do the same thing. Let's just print out what list is. Guess what? There's what it shows you for the contents of your linked list. Again, it's a comma separated collection of your elements inside square brackets, but what's it printing for the actual element? It's printing whatever the toString method for our rectangle returns. Okay, this is like heavily modular. The rectangle is a class, and so an element of this list is a rectangle. It comes with methods, including a way to turn that rectangle into a string, to represent it in a human readable form. And when we say, you know, let's turn this linked list into a string, the code for doing that, the toString method for the linked list, is using the toString method for each of its elements to turn, in this case, each rectangle into one of these strings. Okay? Extreme code reuse, extreme modularization, these are key ideas for this course for object-oriented mindsets. Okay? We're going to leverage this again and again, but particularly in PA2. So if you get fully immersed in this way of thinking about things, the code almost starts to write itself. And it's a wonderful feeling once you get past the kind of novelty of that. If you find that you're writing more and more code and it's getting more and more convoluted, there's a chance that you're fighting against sort of the object-oriented mindset, right? Because if I asked you to make a linked list of rectangles and print it out in this format, right, you might not think that this is all you have to do, right? You might start trying to traverse the list and then like pull out the height and the width and append them with an X in the middle and so on, right? It's not that hard. Right? Everything is encapsulated. So rectangles have a way to print, linked lists have a way to print that use the way that rectangles have to print, and so on and so forth. Alright, so let that kick around in your brains, and that takes some getting used to, right? But let's go on and look at something else. Let's look at HashMaps. So HashMap is another data structure in Java. It takes a pair of type specifiers, so it's generic. And what is a hash map? It's a hash. So we talked a little about hash tables in 222. We wrote some ODPs, I believe, for making hash functions, but we didn't do a full-on hash programming assignment in winter. Some quarters we do. I don't think we did that this quarter. But what's the idea of a hash? A hash is basically an associative array. So what is an associative array? A regular array that we think of, you know, let's just say something like x bracket 5, where this thing is an integer. An associative array, let's just say x bracket anything that we want. Could be an int, could be a string, could be a double. It could even be a rectangle. It could be a linked list, right? So a hash is like an array that we can index with something other than just consecutive integers starting from 0. Okay, so we could say x bracket Izad, x bracket Nick, right? X bracket 3.1416. So there's a pair of things associated with a hash, and we think of these as a key and a value. So hash bracket key equals value. And it's called an associative array because basically for each particular key that we've stored, we have associated with that some value. Okay, and this is nominally a way that memory might work, right? We have some memory that brings up something else, and we can use that and find something associated with that, and we can use that and find something associated with that. That's one way that our minds seem to work, right? It's why you pick up a certain smell and suddenly you're flashing through, 100 memories from your past. So this is an associative array or a hash. And Java comes with, multiple implementations of hash tables. The one we're talking about now is a hash map. And when we have a hash map, we can do a lot of things, but the main things we're going to do are put associated with some key a particular value, or we can say get a value associated with a key, or we can say delete the entry for a given key. And so when we talked about hashes, those were the three main operations: get, put, and delete. So we can store something into our hash by saying put, we can retrieve something with get, and we can remove something with delete. But in practice, there's a lot more you can do with hash maps. So we can clear them to get rid of everything that's inside. There's our get method, there's our put method, there's a remove object, that's what I call delete. We can replace an entry in place. We can say go ahead and find a key and replace its value with this. We can ask how many things are stored in there. And we can also make what's called an iterator, a way to say show me the elements of my hash one entry at a time. And that's important because with an array that starts from 0 and goes through 9, we can get to every element of the array by just saying show me element 0, 1, 2, 3, and so on. With a hash, since we don't know what these keys are, we can't say show me the element indexed by this and that and this other thing, right? So there are methods in the HashMap class for iterating over all the different keys in the hash. We're not going to worry about that for now. But it is something you can do. All right, so when you declare and construct a hash map, you have to specify two things. What type of object is the key and what type of object are the values? Okay, and they can be anything that we want. So this imports from Java utility HashMap. So let's go ahead and write some code for that. So I'm going to import HashMap. I'm going to call this hash, and I'm going to make a hash map. And let's start off with just a hash of strings for the keys and integers for the value. All right, and so this constructs it. And again, we just specify the types of variables right here and right here. And I have to name my hash, so I'm just going to call it H. And so let's put some stuff into our hash, h.put. So we'll We'll just store some numbers. Is cool. And then let's do some gets. So h bracket Nick and we'll do h dot get quote Nick. All right. So H is our hash. We're going to say get the element indexed by Nick, and it should give us 2001. And if we do this, for cool, we should get this. And if we do this for lowercase cool, right, there's nothing in here that's associated with lowercase cool, so we should get back null. Okay, HashMaps return null if you don't have anything associated with that key. So let's compile it and let's run it. And so Nick is 2001, cool is 42, lowercase cool is null. All right, so we can store these things and retrieve them by saying hash.get. And if we try to print this by just appending it to a string, which we'll call the toString method, what do we get for our output? We get this nice representation where, you know, we've got curly brackets and it shows us each key and shows us the integer that it's equal to. Right? And curly brackets, because hashes in some sense aren't ordered, right? Lists are ordered. There's a first element, a second element, a third element, so the lists come out in square brackets. But hashes, there's no guarantee to what order this is going to come in, right? So it showed us hello, Nick, and cool, and we store these in the order of Nick, hello, cool. So it's not clear why it came out in this order. There's no guarantee on what the order of this is when you go through the data. But that's the contents of our hash. Okay, and if we wanted to make, you know, something that stored strings associated with each one, so let me do something that says, you know, Nick is a person and hello is a greeting and cool is an adjective. Let me put my prints back in. So now when I run this, right, I can look up Nick and see that Nick is a person. I can look up cool and see that it's an adjective. I can look up lowercase cool and see that it's not stored in my hash. And, you know, my toString on the hash object just says hello equals greeting, Nick equals person, cool equals adjective. And, you know, you can have spaces and all that sort of stuff. These are just strings, okay? So don't think like bash weirdness where things get broken up by spaces and such. They're just strings, okay? So that's the idea of a hash map, okay? And it's really powerful because, you know, these can be anything that you want, integer strings, or they could be rectangles, or they could be linked lists. So PA2, we're going to make a hash map that's going to be indexed on strings and is going to associate with each string a linked list. And we're going to use this to make a word index program that we can feed War and Peace, for example, and it will make a collection of all the words contained in that document and what position that word is in the document. And so for each word, we'll see a linked list of positions where that word is available. And to do this, you're going to have to actually write very little code. Okay, your whole challenge is going to be figuring out how to use these pre-existing classes and put them together to do what I just described. You're not going to be messing with sentinel nodes. You're not going to be messing with pointers. You're never going to say, this thing next equals that thing previous or anything like that. Okay, it's all going to be about calling methods, constructing objects, and so on and so forth. And this is what a lot of modern programming is. If you've ever done any development of, say, Android apps, this is all you do, right? You very rarely actually write any Java code. It's mostly just calling things that are already pre-existing for you. And it's a really fun way to develop. It just takes some getting used to mindset-wise. But when you do need to actually do some coding, right, you've got lots of experience with that. You know how to do algorithms, how to make loops and conditionals and so on. So you can customize what's happening, but largely you're just picking up blocks and putting them together and making really cool stuff. And it's a lot of fun. So we'll talk about details of PA2 tomorrow. I'll try to post it later on tonight. We'll talk about it tomorrow, and then we'll start looking at some more specific examples of code using some of these classes and thinking about how we can use those to make our index utility. All right, so I will call it quits there. Shoot me an email, come to office hours tomorrow if you have any questions. Otherwise, good luck on PA1, get that turned in, and we'll move on to even more fun and interesting stuff. All right, have a great day. Thanks.